this video, we'll be talking about collision theory. For a reaction to take place, atoms, molecules, or ions must collide. But just because they do collide doesn't mean they're going to react. An effective collision is one that leads to a reaction. An ineffective collision does not lead to a reaction. In order to react, atoms must be close enough to form chemical bonds, but there are several things that influence whether they will, whether the rate of reaction will be fast or slow, and how likely they are to form bonds. Collision theory is based on the following postulates. Postulate number 1, the rate of a reaction is proportional to the rate of reactant collisions. In other words, the more collisions there are, the higher the rate will be. Postulate 2. The reacting species must collide in an orientation that allows contact between the atoms that will become bonded together in the product. If the orientation is wrong, bonds won't form. We have a reaction. 2 carbon monoxide molecules react with 1 oxygen molecule to form 2 carbon dioxide molecules. Now, this is a multi-step reaction, and we're going to look at the first step of this, where 1 carbon monoxide molecule reacts with 1 oxygen molecule to form carbon dioxide and a single unstable oxygen atom, which is going to go on and react in a second reaction that's not shown. Now, in order for this first step to happen, carbon monoxide and oxygen must hit each other in just the right orientation. If they don't, the reaction won't happen. Postulate 3 states that the collision must occur with adequate energy to permit mutual penetration of the reacting species' valence shells so that the electrons can rearrange to form new bonds and new chemical species. If there's not sufficient energy, no bonds will form. In summary, whether a reaction will happen depends on the probability of species bumping into each other with the right energy and orientation. Now let's look at some of the factors that we can vary in the lab that will affect collision rates. The first one is concentration. As the concentration of the reactants increases, there are more molecules available to collide with each other. In other words, there will be more collisions per second, and this will increase the reaction rate. We can also change the surface area by grinding our reactants up. And the more you grind up the particles, the greater the amount of surface area that you will have. And the more surface area you have, the more molecules are going to be able to make contact with other molecules and react. We can also increase the temperature, and as we do, we increase the average kinetic energy. The molecules will be moving faster, and more collisions are going to happen, and this will increase the reaction rate. Now, for most reactions, most collisions don't result in a chemical reaction. Orientation is important, and usually there's some orientations that will result in chemical reactions, and others won't. Now, let's talk about activation energy. This is a picture of a reaction energy profile, and we're going to talk about this in a lot more detail in the next video. But you'll notice we have energy along the y-axis, and along the x-axis we have the extent of reaction. We'll go over what that is a bit later. The thing we're going to look at right now is the energy. Activation energy is the minimum energy that's required to form a product during a collision between reactants. When we look at this graph, you can see A plus B. This is the potential energy of the reactants. And then we go all the way up to the top of a hill. We call this difference in energy from the potential energy of the reactants to the top of the curve the activation energy. And you can think of this as the minimum energy that's required to form a product during a collision between reactants. If the average kinetic energy of the molecules is lower than the activation energy, the reaction will occur slowly, since only a small fraction of the molecules are going to have enough energy to react. Remember, when we think of temperature or when we think of the energy of molecules in a sample, they don't all have the same amount of energy and they don't all have the same velocity. Some of them are moving really, really slow and some of them are moving very, very fast. So in any given sample, some of the molecules are going to be moving too slowly to overcome that activation energy barrier, but some of them have enough energy to do that. And when the average kinetic energy of a sample of molecules is higher than the activation energy, more molecules are going to have enough energy to react, and the reaction will go faster. In a previous video, we talked about the Maxwell-Boltzmann distribution. This curve describes the distribution of particle energies in a sample, with some particles moving very slowly and some moving very quickly. Remember that the faster the molecules in a sample are moving, the more shifted to the right the curve is and the flatter the curve is. And there are a number of things that can influence the velocity, including the mass of the particle. Larger particles move more slowly, as well as the temperature of a sample, since velocity of particles increases with temperature. We can use this curve to get a qualitative estimate of the fraction of collisions that have sufficient energy to lead to a reaction. In a previous lesson, the x-axis was labeled speed, but the axis in this particular diagram is labeled kinetic energy. And remember, energy is closely related to speed or velocity because kinetic energy equals 1/2 the mass times the square of the velocity. Note that at higher temperatures, where the average kinetic energy of the particles is higher, remember that's what temperature is related to, the average kinetic energy. But at high temperatures, a greater fraction of the molecules has sufficient energy to overcome the activation energy barrier, and this is going to lead to a faster rate. We see in our diagram how the yellow curve shows a sample at 273 Kelvin, and this is a very low temperature. So we have a tall peak which is shifted all the way over to the left. When we heat this sample up to 1273 Kelvin, this curve shifts to the right and it flattens out, and this is represented by our blue curve. And the area under the curve is related to the total number of molecules in the sample. And we can see that in that higher temperature curve, we have more molecules with enough energy to overcome that activation energy barrier. So in that higher temperature sample, the rate of the reaction is going to be higher than it is in the lower temperature sample because more molecules have enough energy to overcome that activation energy barrier. Let's summarize. For an elementary reaction to successfully produce products, reactants must successfully collide to initiate bond breaking and bond making events. In most reactions, only a small fraction of the collisions leads to a reaction. Successful collisions have both sufficient energies to overcome energy barriers and orientations that allow the bonds to rearrange in the required manner. The Maxwell-Boltzmann distribution curve describes the distribution of particle energies. This distribution can be used to gain a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction, and also how that fraction depends on temperature.